Welcome everyone to my talk, and thanks a lot to the organizers for inviting me here today. My goal in this presentation is to give you a tutorial-like introduction to our work on physics-based deep learning, where the underlying idea is to mix insights from physics, in particular about the underlying signal propagation dynamics in optical fiber, with novel data-driven optimization techniques. And before I start, I want to briefly thank and acknowledge all my collaborators who have contributed to this work. Effectively, we are addressing the question to what extent tools from machine learning can be used productively in future optical transmission systems. And this particular work actually started with a rather simple observation. Specifically, we started looking into this some 4 years ago, which was the time when a lot of the landmark papers on deep learning had just come out. And what was interesting to us was that the types of computation graphs that you can see in the fiber optics literature, they look surprisingly similar compared to the ones you can find in machine learning, in particular the so-called split-step method for solving the propagation equations in fiber optics. And when we initially started to discuss this, the main question that we had was, is this just a coincidence or is there a more fundamental connection? And this brings me to the agenda of this talk. So in this talk, we show that, well, in fact, multilayer neural networks and the split-step method, they do have the same functional form. They both alternate linear and very simple pointwise or element-wise nonlinearities. And then based on this observation, we propose a physics-based machine learning or deep learning approach, which is ultimately based on parameterizing the split-step method. And unlike a conventional neural network, this is not just a black box function approximator. And then finally, as an application, we revisit the problem of designing hardware efficient nonlinear equalization, and we call this approach learned digital backpropagation. And this is an outline for the rest of the talk. So I will start with a very brief recap or introduction to machine learning neural networks for communications. And then I will talk in detail about this physics-based machine learning approach. And then lastly, I will talk about the application called learned digital backpropagation. And then finally, conclusion. All right, so let's start. And there are, of course, many branches of machine learning. For this talk, we are exclusively focused on supervised learning, where the task is to design a parameterized function f sub theta in order to accomplish a certain task, for example, recognizing handwritten digits. And the way to do that is to first, we have to choose a particular model for this parameterized function. And we are mostly concerned with deep neural networks, in particular deep feed-forward neural networks, which this down here is the graph representation that you commonly find, where you have input neurons, which then get processed with a linear function, and then you get to the hidden layer where they get processed with a nonlinear activation function. So this, I usually use this top representation here, which is more the signal processing viewpoint, where you can see that what the neural network is effectively doing, it's applying a linear or affine transformation, followed by the element-wise application of a nonlinear activation function. And then you would alternate this depending on how many layers or steps this neural network has. Then once you have designed the network, then you can do the training or the learning, which consists of jointly optimizing all the parameters. And the parameters here are the linear steps. So the weight matrices and the bias vectors in the linear steps. To do that, you usually are given a data set where Y here are the model inputs and X are the labels. And then we would simply iteratively minimize an empirical loss function using some form of gradient descent or stochastic gradient descent. And how can we now apply this to transmission design? So the conventional approach to physical layer design is that we start, of course, from the channel model in the center here. And the traditional or conventional approach is that we have handcrafted DSP blocks based on mathematical modeling. So we would start with our data in, and then we have usually add some redundancy to the data, modulation, and so on. And then at the receiver, we would apply reverse operations, for example, equalization, decoding, to hopefully get our data out. What can happen is, of course, that For example, we can have model deficiency where no good model might be available to design these blocks, or alternatively algorithm deficiency where even if we have a good model, the implied algorithms might be infeasible to implement and may require simplifications. And what we can do in this case is that we can replace our hand-designed blocks with function approximators and then learn good parameter configurations from data. So we rephrase this communication problem as essentially a large-scale optimization. And we can do that classically. This is done at the receiver, but recently there have also been other ideas to do this jointly at the transmitter and the receiver, in particular this so-called end-to-end autoencoder approach, which allows you to jointly optimize transmitters and receivers in one optimization step. And lastly, transmitter learning is a little bit tricky because you would need to propagate gradients somehow through this channel. But in practice, so for example, experiments, this is not really possible, but you can then learn, for example, a surrogate channel model, which can then be used to propagate gradients through this. So we have our three blocks here, the transmitter, the channel, and the receiver. And of course, in principle, we could just use neural networks or deep neural networks for each of these blocks. However, the problem, there are many potential problems with this. So one particular is that if you've ever tried this yourself, then usually the first thing that people ask, or students usually ask, is how should I choose the neural network architectures? So for example, the number of layers or the type of activation function and so on. Because depending on the problem, there are no real guidelines for this. So it becomes a trial and error, which is quite unsatisfactory. Another common problem is how can we limit the number of parameters, because neural networks usually, if you increase the size, they tend to quickly blow up in terms of complexity, for example, in terms of the number of operations they require. And lastly, even if we have found a good solution and everything seems to work well, it's not always clear how to then interpret the obtained solutions, or are there any insights that you gained about the particular problem. And the contribution of our work was to, rather than immediately jumping to like conventional neural networks, is we design something which I call a neural network-like machine learning model, in particular by exploiting the underlying physics of the propagation. So how does this work in more detail? So we start from the nonlinear Schrödinger equation, which describes how the input signal evolves as a function of the distance to get the output signal. And this is a partial differential equation, which has no closed form solution in general, but we can rely on numerical methods, in particular the split step method or the split step Fourier method, where you divide the fiber into short segments, and then you assume that in each segment, the effect of these operators there can be separated. And then you end up with a computation graph that looks like this. So you have your transmitted signal here, and then you apply a linear operation corresponding to chromatic dispersion and an element-wise nonlinearity corresponding to the optical Kerr effect, which introduces a nonlinear phase shift. And then you alternate depending on how many layers or steps you have. And now with this kind of notation, going back to this original observation that we had, we can now actually compare this a little bit more closely side by side. So on the one hand, we had neural networks, which were these simple parameterized functions. And then on the other hand, we have the split step method. And if we put them side by side like this, then you can see that, well, this almost looks like a neural network. So the split step method also alternates between linear transformations and element-wise nonlinearities. There are some differences, of course. So for example, in the conventional neural networks, you process real valued signals, and these activation functions are usually real valued, whereas in the split step method, they're complex valued, but mathematically, they both alternate linear and element-wise nonlinearities. And then what the main idea of the method that we proposed was to then say, okay, rather than using a neural network, let's start from the split step method that we are familiar with, and now let's completely parameterize this. In particular, parameterize all the linear steps. And what this gives us, it gives us now a parameterized model, where we can train all these linear steps in a joint manner. And interestingly, this kind of approach nicely generalizes a lot of problems or a lot of approaches that people are well familiar with. So for example, what you would typically do in conventional split-step methods is, for example, step size optimization, which is included here because all the linear steps are completely parameterized, but also nonlinear operator placement, where you would usually optimize this gamma parameter here a little bit by hand, is also included because you can always absorb this as a scaling factor in these in the linear filter steps. So the question is, so as of now, I only introduced the parameterized model. So the question is now, how can we apply such a model in practice? And going back to this block diagram where I had the physical layer transmission systems, I would argue that you can, in principle, at least apply this in each of these 3 blocks. The only thing you have to make sure, of course, is that you are in an optical scenario where this, the Schrödinger equation is a good approximation for your channel. So the most obvious is maybe the channel, because so far I actually only talked about the channel modeling. But now, since you have parameterized the channel model, you could, for example, fine-tune it with experimental data and, for example, reduce simulation time. We will, in the remainder of the talk, exclusively focus on the receiver here, so in terms of a nonlinear equalizer. But in principle, you could also apply it at the transmitter as a predistorter. And in fact, some people argue that you should do a split approach where you do half at the transmitter and half at the receiver. Before I go in detail into the application, just to talk a little bit about the potential benefits that we would expect from such a method compared to using like a standard black box neural network approach. So one has to do with the network architecture choice, because a lot of the questions or issues that we previously had, they now almost become trivial. So for example, the activation function in this approach is fixed, so there's nothing to choose. The number of layers is equal to the number of steps, which is good because we have a relatively good understanding for how to choose a good number of steps to get a certain accuracy that we want to have. Also, the hidden feature representation in this model, they have a correspondence to the signal at intermediate fiber locations. And parameter initialization can be done in such a way that at the start of the optimization, we're equal to the conventional split-step method. So we cannot never do worse than conventional split-step method approach. In terms of complexity, what's interesting about this approach is that we have embedded the propagation dynamics kind of into the model. So we don't need to relearn things that we already kind of expect from the channel, how the channel behaves. Also, we will see that we can reduce complexity by exploiting filter symmetry, which can be enforced in the linear steps. And we will apply other approaches, model compression based on parameter pruning and quantization. And lastly, we will also show examples where we were able to actually give an interpretation for the learned solution, so that there are kind of explanations for the benefit compared to previous handcrafted solutions. So with all of this said, let's now go a little bit more into the application, and we're going to focus on nonlinear equalization in the form of digital backpropagation or learned digital backpropagation. So the idea of digital backpropagation is, of course, to invert the Schrödinger equation at the receiver. And the problem here is that this is widely considered to be impractical. And the argument is fairly simple, that, well, just doing linear equalization is already one of the most power-hungry blocks implemented in coherent receivers. So I really like this paper where they designed a transceiver chip. And you can see from the chip layout, kind of the importance, or like the complexity in terms of area or power consumption. So here, this chromatic dispersion, one of the largest blocks. And when people hear digital backpropagation, where you have to do many linear steps, then this is probably what people think. So this is clearly impractical, because we would have to do, many of these big steps on the chip. The conventional approach would be to limit the number of steps, so kind of reduce the number of steps as much as possible. And this seems fairly intuitive at first. However, from a machine learning perspective, what you are doing is basically you flatten a deep or multi-layer computation graph, which some people argue is actually not that good of an idea, at least if you want to have a good, accurate solution with low complexity. Our approach is a little bit different. So what we are trying to do is we're trying to still use many steps or many layers, but we do a model compression step where we, at each individual step, try to get the complexity down as much as possible through a joint optimization, pruning, and quantization approach. So how does this work? Well, we call this learn to backpropagation, and what we did is we implemented this split step computation graph in TensorFlow, where now all these linear steps are parameterized, and in fact we further constrain all of these matrices to be equivalent to standard FIR filters, and we further enforce these filters to be symmetric. So the number of parameters is now roughly reduced by half because we only need to learn like 1/2 of the filter coefficients. So now the task becomes to jointly optimize all these filter coefficients in all of the M steps. And we do that in a fairly standard approach. So this is a fairly standard deep learning approach where we fix a loss function, particularly the mean squared error, at the output of the equalizer. And we use a standard deep learning optimizer here, the Adam optimizer, with a fixed learning rate. What's not so standard is maybe the pruning approach, where we're trying to compress this model, and we do that by iteratively pruning the outermost filter tabs during gradient descent. So to illustrate how this works, so these are all the filter coefficients that we want to optimize, and here's they're just written out, and we only have to look at half of them because the other half is symmetric. So we start with relatively long filters, and in fact we're initializing this to kind of least squares chromatic dispersion filters. And then we set a certain target length that we want to achieve, and then we just throw away the outermost filter tabs until we hit our target length. And the way this looks like in the optimization looks like is that we start from a certain effective SNR, so the inverse of the mean squared error, and then whenever we prune, we would get a performance penalty, but you can see that we quickly recover and keep improving our model until we hit the next filter. And you can prune quite aggressively, yeah, but